This presentation is about the representation of data in computer systems converting between binary and denary. A question is often asked, who is smarter, a human or a computer? Well, in reality, a human can process a much greater variety of information in different ways than a computer ever can. The benefit of a computer, though, is that it can process information very quickly. Computers are simple in the fact that they can only translate two electrical signals, 1 meaning on or 0 meaning off. The numbers 1 and 0 are known as binary. In this video we're going to learn how to translate binary numbers into denary values, but before we go any further it's worth briefly mentioning a few storage terms. So ones and zeros. A 1 or a 0 is known as a bit. A combination of 8 ones and zeros makes up a byte. Other terms that you might have come across are things like kilobytes, which is actually 1024 bytes, a megabyte, 1024 kilobytes, a gigabyte, terabyte, petabyte, and so on. When we learnt to count, we learnt in denary. This means to the power of 10, probably because we have 10 digits on our hands. So, if we take the number 2163, if we were to count this out, this means 3 ones, 6 tens, 100, and 2 thousands. As discussed earlier, binary means either a 1 or a 0, and therefore only has 2 values rather than 10. This means that to work out a binary value, we need to work to the power of 2. So instead of ones, tens, hundreds, and thousands, we then go up to the power of 2, which is 1, 2, 4, 8, 16, 32, 64, and 128. So now we're going to learn how to make denary numbers into a binary number a computer can understand. So we'll start off with a small number such as number 13. Starting from left to right, we look at the table and say, are there any 128s in the number 13? Well, there aren't, so we put a 0. 64, again, a 0. 32, no, a 0. 16 is greater than 13, so again, a 0. Now, there is an 8 in a 13, so we're going to put a 1. 8 and a 4, yes, that makes up 12, so we put another 1. 8 and 4 and a 2 makes up 14, so that's not right. And then we add another 1 there, because 8, 4 and a 1 make up 13. So the binary representation for the number 13 actually is 00001101. Let's try that theory with a larger number such as 210. So are there 128 and 210? Yes there is, so we add 1. Plus 64, that makes 192, so we'll add another 1 there. If we add 32 to 192, that will give us 224, so we can't bust, so we put a 0 there. So working on 192, we're going to add 16, which gives us 208, so we add a 1, so we haven't gone bust yet. So that leaves us with only 2 left, so we put the 1 in the 2 and fill the rest with zeros. So the binary representation for 210 will be 11010010. Now let's try converting binary into denary. So here's a binary value, so if we take the 128 and then we add on the 16, that would actually give us 144. If we then add on another 8, that would then give us 152. Now all we've got left to add on is another 1, so that will give us 153. So the actual denary value for this binary number is 153. That was converting numbers between binary and denary by the Dunn Johnston IT department.